Hey kids, welcome to 14.3, partial derivatives day 1. Yes, it is going to take us a couple days to get through partial derivatives. Partial derivatives are exactly what they sound like, doing derivatives in parts. Now you might ask, why would we do such a thing? Well, recall when we took Calc 1, there were times at the very beginning of the year where I asked you to estimate the derivative from a table. So given the temperature and heat index here, heat index is apparent temperature. Look at I'm giving you just two variable function, right? Calc 1, temperature and G of T. But when the relative humidity is 70%. So I need you to think about this. This part here, humidity is not part of this table, but I'm telling you, right? This is temperature and this is heat index, apparent temperature. But I'm telling you that this data was taken when the relative humidity was constantly 70%. And of course, you could estimate the rate of change at 96 degrees, right? By just saying, well, the slope of the tangent is approximately, right, 125 minus 118 over 96 minus 94, which is 2. So that is approximately 3.5 what? 3.5, right? Heat index per temperature, right? Heat index per degrees. Now look at this next table. Given relative humidity values and heat index, which is apparent temperature values, when the temperature is held constant. And forgive some of the writing and ambient noise here. I am in a car driving back from Boston. Estimate the rate of change at 70. Well, you would do the same situation, right? And you'd say the slope of the tangent is approximately 125 minus 121 over 5, right? Which is approximately 0.8-ish. 0.8-ish what? Right, what do I have here? Heat index per humidity. So think about what you just found. You just talked about finding the derivative. The derivative here, you found G prime, but you found G prime when the humidity was constant. You also found a derivative here, G prime, when the temperature was constant. So if I define a heat index function in terms of both the temperature and relative humidity, right? So I have a function in terms of temperature and relative humidity, I can still talk about those separate rates of change. In parts though. So the rate of change of temperature when the relative humidity was held constant, you estimated that at 96 when the humidity was constantly 70%, and we estimated 3.5. Then I said, what about holding the temperature constant? What is the rate of change when the temperature was constant? And you estimated that with 96 held constant and estimated at 70, and you got approximately 0.8. That's the idea behind partial derivatives. When you have a function defined in two variables, find the rate of change of one variable while holding the other one constant, right? So that's what this says. Look at this notation. The partial derivative with respect to x, see how x is down here, sub x, of a function in xy is a limit. That is what derivatives are. They are limits. But notice it is a function in x plus h with y held constant. Y held constant. The partial derivative of f with respect to y is a function, hold the x constant, change the y. Here's your delta y. Hold the x constant. You do not have to worry about this definition or even working with this definition. Depending upon the level of, or where you take multivariable in college, they will probably do epsilon delta proofs with this, just like they do with epsilon delta proofs in Calc 1 in college, but that is not part of the AP calculus curriculum, and so we are not going to do it here either. What you need to know is if we have that two variable function, right, we can call it z, then the partial derivatives have the following notation. So all of these notations are valid. This is the one I tend to use the most, right? I say partial derivative with respect to x. Sometimes it is partial derivative with respect to x, and they tell you the function is in what two variables the function is in terms of. This is also fairly common. This is called del. That letter, it's called del. The partial derivative of f with respect to x. Or the partial derivative with respect to x of the function in terms of two variable. Sometimes we have three variables, del z, right? The partial derivative of z with respect to x. Right? Sometimes they use this, I don't use this notation very often. Sometimes they use the first derivative here, partial with the first variable. Right? I don't use this very much at all. Meh. We can also then, of course, take the derivative with respect to a second variable, right? Partial y. Del y, right? Del f with respect to y. Then, of course, we could also do with respect to z, if we have the third variable, right? Partial z. So let's do a couple. Find the first partial derivatives of this two-dimensional, right, two variable equation here, right? So my domain is 2 space, and my figure is up there in 3 space, in my z space. Find the first derivative of f with respect to x, which means hold y constant. So treat y cubed as, 8, and treat y as 2, right? Pretend they are constants. So how do you take the derivative of a constant times x to the 4th? Right. The derivative of x to the 4th is power down, bring the 4 down. Take the 4 down, x, subtract 1 from the exponent, times this constant, right? Remember, this is just a constant. How do you take derivative of 8x squared times a constant? Well, it's that constant times 8 multiplied times the 2 that you're bringing down. So that's 16 times the constant y times x to the 1st, right? Y was the constant. But now hold x constant. So partial y, right? The derivative of f with respect to y means hold x constant, right? Well, my circles didn't move all that well. So what does that mean? X to the 4th is a constant. Pretend it is, 16. Pretend x, right, this x here, x squared is, 4, right? So how do I take the derivative of y cubed? I bring the 3 down. bring the 3 down in front, times this constant x to the 4th, and then y to the subtract 1 from the exponents. This is a y to the 1st, right? How do you take the derivative of a constant times y to the 1st? You bring the 1 down, copy the constant over, and then that's technically y to the 0, which is why you only see 8x squared. Crazy, right? Let's try this one. This time I gave you 3 I gave you 3 variables. So my domain is 3 space, and I'm going up in somewhere into 4 space, right? So can you take, and I use the del notation this time, partial derivative of f with respect to x, which means you're holding the y and the z stuff constant. So what's the derivative of x squared times a constant? 2x to the 1st times that constant. Hey, I forgot to circle the y. What's true about this whole term? If y and z squared, they're both constants, what's the derivative of a constant? Bye-bye. And what's the derivative of sine x? Now take the partial f with respect to y. If I'm differentiating with respect to y, this time I am holding right? X squared is a constant. Z squared is a constant. Sine x is a constant. So what is the derivative of y times a constant? That constant. What's the derivative of y times the constant? That constant. What's the derivative of a constant? 0. Now let's take the partial with respect to z. Who's constant? X squared and y are constant. Y is a constant. Sine x is a constant. What's the derivative of this whole constant? Nothing, honey. What's the derivative of z squared times a constant? Bring the 2 down, copy the z over, subtract 1 from the exponent, times that constant. And I'm only just going to put it here in alphabetical order, right? Alphabetical, right? You don't have to do that. And then what's the derivative of a constant? Nothing, honey. Done and done. And done, I guess, right? We did 3 of them. Well, this should scare you a little bit. Because if I can ask you for the first partial derivative, guess what else I can ask you for? Higher order derivatives, right? So to find the higher order derivative, you just have to be super careful about your notation. I do have to find each one of them in parts. Notation matters. Oh, my Lanta, look at this. So notice the parentheses, and sometimes these parentheses aren't written, but I find them super useful. So if you have a function f in terms of 2 variables, taking this is already one derivative. I've taken the partial with respect to x. If I take the partial with respect to x, and then I also want to take the next derivative, second derivative with respect to x, it is sometimes written this way. I like the parentheses. It is also in del notation written not this way. You don't see it this way, but you do see it this way. Notice it's here, the second derivative with respect to x. In this notation, here's where this is what you're looking for. You're looking for, hey, first I was taking the derivative with respect to x, and then I'm taking it with respect to x again. Look at this notation. First, I took the derivative with respect to x. Now I'm going to take it with respect to y. That's what this means. But notice my del notation. This you have to read, right? I read my derivative notation from left to right. Here you need to read it from right to left. This is telling you you took the derivative with respect to x first, and then you want to take it with respect to y. Here, read from left to right. You took the derivative, the partial derivative of f with respect to y, then x. But in the del notation, you need to read it this way. I took the derivative, partial derivative with respect to y, then x. Okay. So partial y, then y again. Partial y, then y again. All right, order matters. Watch the note, how the notation is presented to you. Oh, my Lanta. Right? Here's the third derivative. Again, order, your notation really matters. Right? This was, I took the derivative of partial f with respect to x, then y, then I'm going to do x again. So again, you got to read this one this way. Partial x, then partial y, then partial x again. Took the partial derivative with respect to y, then with respect to x, then with respect to x again. Here, started with the first derivative in terms of y, and then in terms of two x's. X and then x again. So let's try one. Find all the second order derivatives for this function in two variables. So I'm going to do on the left the partial x's. Right, so I already did the first one. Do you see where that came from? I'm holding y constant. So this first term had no y's in it, so the derivative of cosine is negative sine, but I had to use the chain rule with the 2. Here, e to the 5y is just a constant. How do you take the derivative of x squared? Right? 2x to the first times the constant. And then this is just a constant. 3y squared is a constant, so its derivative was 0. Then I held x constant. When I took the first derivative with respect to y, this term only has an x in it, so that cosine of 2x is a constant. The derivative of a constant is 0. X squared is a constant. What's the derivative of e to the 5y? Well, it's 5 times e to the 5y. Here's my negative. X squared is just a constant. And now there is no constant here. This is just what is the derivative of 3y squared. So now I'm going to do the derivative of, I have to do the second derivative of the first derivative in its parts, right? The first derivative with respect to x, but now take its derivative with respect to x. So I am holding y constant again, so the only y value is over here. Right, and what happens here, this is just going to be, right, the derivative of negative 2x times a constant is just negative 2 times that constant. Now go back to this original, but take the derivative with respect to y, so you're holding x constant. Right? So you're going back, you're not working with this blue function, you're going back to partial x and taking the derivative with respect to y. Well, this whole term has only x's in it, so that's all a constant. The derivative of a constant is 0. And now you're taking the derivative of e to the 5y, right, with a constant in front of it. So that's 5 e to the 5y times that constant. Right? So now let's go, so that's half of the problem. Let's go back. And given the partial of f with respect to y, right, do you see where I got that from? Hopefully, right? Talked about, well, we already talked about that. So now I need to take that partial y and take the derivative with respect to y. Then I need to take that same partial y and take the derivative with respect to x. So first I took the derivative with respect to y, which means I'm holding x constant. So this negative 5x squared is going to stay. And then I'm just going to take the derivative of e to the 5y. Right? The derivative of 6y with respect to y is just 6. Now, I'm not going to go to this blue. I'm going to go back to the, right, back here to the partial with respect to y, but take the derivative of this one with respect to x, which means I'm holding the y's constant. So the derivative of negative 5x squared is times a constant is negative 10x to the first times that constant. And then 6y is a constant with respect to x. And so that derivative is 0. Hey. Oh, gosh, darn it. I didn't mean to erase that. But did you notice after all of that work, we got these two to be the same? Negative 10x e to the 5y, negative 10x e to the 5y. Clairaut, Alexis Claude Clairaut, a Frenchman, his theorem says, if your derivatives are continuous, then this statement will always be true. Partial x with respect to y will always equal partial y with respect to x. In terms of x, taking the derivative in terms of x, right? Pretty cool. So that's kind of a neat theorem. Oh gosh, let's do this one. All right, three variables, right? So my domain is the 3 space, and I'm graphing something up in 4 space. Can't even imagine what that looks like. But look at the notation I'm giving you, right? Remember, you need to read that left to right. So the first thing you need to do is partial in terms of x. So partial in terms of x, right, means that I've got the only thing in terms of x is here, right? ln x So z cubed y squared is just a constant. A constant times ln x, the derivative of a constant times ln x is that constant. Times the derivative of ln x, which is 1 over x. Now, take that expression and take its derivative with respect to x. Right? So remember now, this is still a constant. With respect to x, I have x to the first, or if you want to pop that up here, x to the negative 1. Z cubed and y squared is still a constant. So the derivative of a constant times x to the negative first is that negative constant times x to the negative 2. Right? So now I've done now I'm going to take that expression and take its derivative with respect to y. So now I have to focus just on y, and everybody else is a constant. So what's the derivative of a constant times y squared? That constant, bring down the 2, y to the first. Right? Check. Now I have to take that expression and I need to take the derivative with respect to z. So everybody else is a constant. The derivative of a constant times z cubed is, bring down the 3 and multiply it times the constant. Subtract 1 from the exponent. Now I have to take that expression and hold z constant again. What's the derivative of a constant times z squared? Bring down the 2, multiply it times that constant. I don't really care the order of your right? I'm sure if it was multiple choice, it would be in alphabetical order, but I don't care, right? That actually looked pretty devastating, but it really wasn't that bad, right? As long as you focus on the variables that you are not taking a derivative with respect to, all being constants. Here's another example, just with 2 variables, thank goodness, but I gave you the alternate notation. So remember, you've got to read that the other way. So notice I read that, but I really like this notation better. So I started here and I said the first derivative I did was with respect to x. Then I had to do with respect to x again. Then I had to do with respect to y, right? So here's my first x. Here's my second x. Here's my y. Oops, I don't know why I have that over twice. Sorry. So what is my first derivative with respect to x, right? Holding, right? I only focus on x, so pretend that's e to the 2x. What's its derivative? Right? Think of your y as a 2. It's just a constant. So y e to the xy. Now I have to take that expression and take its derivative with respect to x. Now be careful. looking at x. So this partial x with respect to x right? I got to bring the y down. Right now, what if you had thought, oh my gosh, I got to use the product rule? Well, then you would just do this, right? You would say, oh, well, that's plus, so that's the first function. Let's see, I'm not messing this explanation up. I'm e to the xy, right? It's the derivative of e to the xy with that as a constant. But if you try to think you needed to do the product rule, when you took the derivative of this, wouldn't you get 0? Right? Because that's the derivative of a constant. So you would have gotten just plus 0 anyway. So I'm sorry that if that confused you, but I was trying to do a little bit of foreshadowing. Because now I have to take the derivative of this with respect to y. There I am going to have to use the product rule. Do you see why? Ha, pun intended. Do you see why? I have a function here. Y is not a constant. Y is not a constant, and there is multiplication between there. So the derivative of y squared is 2y. Right, so e to the xy times the derivative of y squared plus y squared times the derivative of e to the xy in terms of y. So that's going to be, bring the x down, right? Multiply times the x as being a constant, e to the xy. Okay. So when we're together, I am going to do a little, I'll show you some graphical analysis of what we're doing with these partial derivatives. Okay. It's pretty cool. I will see you later.